Let's look at a couple examples of how to sketch cubics. So we've got a cubic here and it's already factorized for us. Normally you might have to factorize it yourself using the factor theorem and polynomial long division, but in this case it's already done for us. So to sketch this we need to find the x and y intercepts. So let's find the x intercepts first, and to do that we have to make y equal to 0. That means that x minus 1 times x minus 3 times x plus 2 is equal to 0. You can see straight away from here that the x-intercepts are going to be at 1, 3, and negative 2, but I'll just go through the entire working this first time around. So you would use the null factor law, which says that when you've got three things multiplied together to give 0, one of them must be equal to 0. So either x minus 1 is equal to 0, or x minus 3 is equal to 0, or x plus 2 is equal to 0. Should have left a bit more space between these three lines, so I'll put commas here to indicate that they're separate lines. And if you solve for x in each case, you get x equals 1, x equals 3, and x equals negative 2, right? So we can draw that on our graph. Let's draw a rough scale. So our intercepts are going to be at negative 2, 1, and 3. We also know that the graph is going to be shaped like that rather than like that. In other words, it's going to be a cubic that eventually goes up, or it's going to be a positive sloping cubic. And the reason we know that is because the coefficient of x cubed, when you expand all this, is going to be positive, right? You know that this is going to be x cubed plus blah blah blah. The key here is that the coefficient of x cubed, which is 1, is positive. And you know that because the coefficient of all the x's here are positive. So when you expand them, the coefficient of x cubed will also be positive. So sketching this, we can see that it's going to look something like this, right? Sort of missed that x-intercept there. There we go. One thing to note is that this sort of seems like the turning point is right on the y-intercept, but we don't know that. It could be slightly off, sort of like that. The turning point could be, somewhere here. So just be careful when drawing it. Don't make any assumptions about where the turning point is. Okay, we've done that. We need to label the x-intercepts, which are negative 2, 0. This one is 1, 0, and we've got 3, 0. And the last thing we need to do is find the y-intercepts. To do that, we make x equal to 0, and what do we get? We get y equals negative 1 times negative 3 times 2, just subbing in 0 into this formula. And what do we get? We get 6. So this point here is 0, 6. Awesome. Next example. We've got another example here, and we're going to tackle it the same way. So we're going to start by finding the x-intercepts. To do that, we make y equal to 0, right? What does that give us? X minus 4 times this quadratic is equal to 0, right? Okay, now before I use the null factor law, I'm going to factorize this quadratic further. In the previous example, it was fully factorized, but in this case it isn't. And this is actually a perfect square. It's the same thing as x plus 2 all squared. And if you're not convinced of that, you can expand it yourself and see that when you expand this, it gives you that same thing there. So in other words, we can write this as x minus 4 times x plus 2 squared is equal to 0. Now, I'm going to use the null factor law again for this one. I'm going to show you the long way of doing things. So either x minus 4 is equal to 0 or x plus 2 squared is equal to 0, right? Solve both of these for x, we get x equals 4. What about this one? We need to get rid of that squared sign first, so I'm going to take the square root of both sides, okay? The square root of the left-hand side is x plus 2. The square root of the right-hand side, well, the square root of 0 is just 0. And if you rearrange for x, we get x equals negative 2. So we only have 2 x-intercepts for this one. What does that mean? Well, let's label those 2 intercepts first. So we're going to have one at x equals negative 2, and another one at x equals 4. Now remember, your cubics can come in two shapes, right? They can either have two turning points, looking something like the one we had before, or they can have a point of inflection, which will look something like that. And it can either be a stationary point of inflection or a non-stationary point of inflection, okay? Now, looking at this graph, it can't be this option, because if it's a point of inflection, it has to have only one intercept. There's no way it can have two intercepts. For example, you can have something like this, right? But because it doesn't go back down, this graph doesn't go back down, there's no way it can touch this point. So we know that it's not going to look like this shape with a point of inflection. Instead, it's going to have two turning points. Okay? Now, in fact, this repeated factor here, right? I say repeated factor because we have got, so this is a repeated factor, right? It's a repeated factor because you can sort of think of it in another way. You can say x plus 2 times x plus 2 is equal to 0, right? I've just sort of, instead of writing x plus 2 squared, I've written x plus 2 times x plus 2, which is the definition of x plus 2 squared. And using the null factor law, this gives us x plus 2 equals 0, or x plus 2 equals 0. This is x equals negative 2, or x equals negative 2. That's why we call it a repeated factor or a repeated solution, because it's repeated twice, right? Because we have two factors that are the same. Okay? And when we have this, that means that this solution represents a turning point on the axis itself. That means that at x equals negative 2, because this is a repeated solution and it's repeated twice, that represents a turning point here. So this is going to be a turning point. It's either going to look like that or like this. Okay? And this is just a normal intercept because it's not a repeated factor. Okay? Now, how do we decide which one it is? Is it going to be like that or like that? Again, we need to look at the coefficient of x cubed when we expand this. When we expand this, because we know that the coefficient of this is positive and the coefficient of this is positive, the coefficient of x cubed will also be positive. In fact, this is going to be 1 because this is the coefficient of this is 1, the coefficient of this is 1. So when you multiply both of these, you're going to get 1, right? And then you're going to get some other terms there, but we're only concerned with the x cubed because that's the highest power here. And because that's positive, we know that the graph is eventually going to go upwards like that, not downwards, right? So using that, we can sort of extrapolate whether it's going to be shaped like that or that. So we know it's going to go up to infinity, to positive infinity, so it's going to look something like that, which means that this turning point has to be a local maximum. So it has to be a maximum turning point rather than a minimum turning point. And joining the two, we get something like that. Okay? And we need to find the x-intercepts, which we've already found, but we need to label them. So this is negative 2, 0, and this is 4, 0. Okay? In this case, what would the y-intercept be? I'm running out of space. I'm going to do it really briefly here. So the y-intercept is when x equals 0. So that will give us, instead of using this is a bit messy. Oh, actually, that's fine. I'll use that. So x equals 0, sub that in, we get negative 4 times 0 plus 0 plus 4. So we get negative 16. That means that this point is 0, negative 16. Okay? Here's our next example. We've got y equals x minus 5 cubed. Let's find the x-intercepts here. Really, really simple. Don't even have to think about this. What is it? X minus 5 cubed is equal to 0. Okay? Now, again, I'm going to do this the long way just to show you what's going on. I'm going to rewrite x minus 5 cubed as x minus 5 times x minus 5 times x minus 5. Okay? That's just the definition of something cubed. So, what does this mean? Using the null factor law, this means that either x minus 5 is equal to 0, or x minus 5 is equal to 0, or x minus 5 is equal to 0, right? It's the same thing. X is equal to 5, x is equal to 5, x is equal to 5, right? I just want to emphasize that each of these comes from an individual factor, right? So because this factor is repeated thrice, That's why I've done this 3 times. Now, we saw that if a factor is repeated twice, if it's repeated 2 times, we get a turning point on the x-axis. What happens if a factor is repeated 3 times? Can you guess? Okay, if you guess that we get a point of inflection on the x-axis, you're right. And that's exactly what's going to happen here. So we're going to get a point of inflection at this point. Now, the thing to think about is whether it's going to be like that or like that. And we know in this case it's going to look like this, because the coefficient of x, when you expand everything out, is going to be positive, which means that the graph has to go to positive infinity as x goes to infinity. So as x gets larger and larger, y is also going to get larger and larger in the positive direction. Okay, and this point we have to label, it's 5, 0. Okay, we also need to find the y-intercept. I'll do it really quickly here. The y-intercept is when x is equal to 0, which is -5 cubed, which is -125. So this point is 0, -125. Awesome. Next example. So x intercepts are when y equals 0. Okay, that means that x plus 2 squared times 5 minus 2x is equal to 0. Okay, now I'm going to take a shortcut here. I'm going to say x is equal to -2, or 5 minus 2x is equal to 0. Okay, how have I taken this shortcut? Well, I've just omitted the lines where I've explicitly stated that I'm using the null factor law. So what comes in between here would be x plus 2 squared is equal to 0, or 5 minus 2x is equal to 0. Now this line I've written here, and I know that when I solve this I'm just going to get x equals -2, so I haven't bothered to write that part out. Okay, the reason I have bothered to write this one out is because it's a little more confusing. It's not straightforward to see what x will be, so I want to rearrange it manually. When I do that, I get -2x equals -5, x is equal to 5 over 2, or in other words, 2.5. Doesn't matter how you want to think about it, they're the same thing. So let's label those two on here. We've got -2, which is here, and we've got -2.5, which is going to be here. Alright, so that's going to be here and here. Okay, now again, we know that x plus 2 is a repeated factor, and it's repeated twice. Because this is repeated twice, there's going to be a turning point at x equals -2. This is going to be a turning point. Okay, now let's think about which direction the graph is going to go in ultimately as x gets bigger and bigger. This is not the same situation as before. Here we've got a negative coefficient of x here and a positive coefficient here. Now if you expand this out, the overall coefficient of x cubed is going to be -2, which is negative, right? And because of that, the graph is going to go in the negative direction as x gets bigger and bigger. So let's draw a graph based on that. So I'm going to draw this part going down here, and I know that this now has to be a local minimum, or a minimum turning point. Okay, it's not the best drawing, could have smoothened it out a bit, but that's okay. This point is -2, 0. This point is 2.5, 0. Okay, and you also need to label this y-intercept here, but I'm not going to do it. I'm going to move on to the next example. This is our final example, and you'll notice that I have 2 graphs set up here. That's because we're going to consider 2 examples, or 2 possibilities of what this could look like. So we've looked at something similar to this before, where we had a linear factor and then a quadratic factor, and what we did was we factorized this quadratic further. Okay, in this case, however, we can't do that. Why is that? It's because if we consider the discriminant, it's going to be negative. Let's see that. So the discriminant is b squared minus 4ac. When we sub in a, b, and c, we get 2 squared, which is 4, minus 4 times a, which is 2, times c, which is 1. And that's going to be 4 minus 8, which is going to be -4, right? And because the discriminant is negative, this means that this quadratic has no solutions or no factors, right? It has no solutions and no factors. So if we, I'll use the space in the middle here. If we were to find the x-intercepts, we'd make y equals 0, right? And we'd have x minus 2 times 2x squared plus 2x plus 1 equals 0, right? So either x minus 2 is equal to 0, or 2x squared plus 2x plus 1 is equal to 0, right? This has a solution. This is x equals 2. But this does not have a solution. Why? Because we just found out that the discriminant is negative, right? So therefore, no solutions. Okay? And if you were working this out, if you were doing this working in a test situation, this would be acceptable. This is sort of how you would work it out. You might get to this point. It might not be immediately obvious that there's no solutions to this. You might get to this point. You might try factorizing it, and you might come into difficulty. So then you might try finding the discriminant, and you'll see that it's negative, and then you can write that there's no solutions. Okay? But what we're interested in here is what the graph is going to look like. So we know that there's one x-intercept, which is 2. Right, so there's going to be one x-intercept here. Right, that's simple enough. Why do I need to consider 2 possibilities? Isn't it really simple? We know that eventually the graph is going to, because the coefficient of x cubed is going to be positive when you expand all this, we know that the graph is going to go towards positive infinity. So won't it just look like something like this? Right, isn't that really simple? Why am I making it so complicated? And we'll also obviously have to label that intercept there. But the reason I've drawn 2 graphs is that is not the only possibility. There is another possibility of a cubic graph that gives us an x-intercept at 2, 0. What is that possibility? It's something like this. Instead of having 2 turning points, remember, we can also have a single point of inflection. So what if we had something like that, right? And that maybe that's our point of inflection there. This also satisfies the constraint of having an x-intercept at 2, 0. Okay. How do you differentiate between these 2 graphs? How do you tell which one it is? Well, you can't until you use calculus, right? Calculus is a topic we'll cover a bit later, and that will allow you to find the turning points, the coordinates of these of the turning points of any cubic, any quartic, any polynomial whatsoever, right? Once you can do that, you can see how many turning points the graph has. If it has 2 turning points, it's going to be this. If it only has 1 turning point, it could be this. If it has no turning points, it could be something like this, but with a non-stationary point of inflection instead, right? That's going to get messy, so I won't draw that. Actually, I will. So right now I drew it with a stationary point of inflection, but I could have also drawn it with a non-stationary point of inflection. Okay? Yeah. So that's a non-stationary point of inflection there. So you can see that there's 2 possibilities. And to better illustrate this, I've got this web app open. So this is called Desmos. It's a graphing calculator there. And you can see that I've got an equation set up, and which is exactly the same as our equation, right? Our equation was x minus 2 times some quadratic, and similarly here I've got x minus 2 times some quadratic, okay? And I can change those parameters here. I can slide these along and see how the graph changes. And right now it's set up to exactly what we had it. A is 2, B is 2, and C is 1, just like in our question. And you can see that based on what that graphing calculator tells us, it's going to be this option for this particular example. But I'm going to show you that it doesn't always have to be that way. So if I slide these values, you can see that so I'm going to have to adjust the screen as I do this, but you'll see that it's getting, the turning points are getting closer and closer together until they become a point of inflection there. So that's just to show to you that if we have an equation of this form, we're not always going to get 2 turning points. It could be a point of inflection as well. And we won't be able to tell which one it is until we cover calculus, which we will do a bit later in the year. Okay? So I hope that gives you a better understanding of how to graph cubics and the various possibilities that we can have for how graphs look like.